Hello, my name is Russ Timpson. I'm the founder of the Tall Building Fire Safety Network. What you're about to see is a video from our 2025 Tall Building Fire Safety Conference. You can find more other great videos on tall building fire safety on our YouTube channel, and there are many more presentations on our website, www.tallbuildingfiresafety. If you find our videos and presentations useful, please like and subscribe us on our YouTube channel. Halfway through the video, you're going to see details of our 2026 conference, which will take place in May in London. We have a fantastic program, and we also have a separate high-rise firefighting masterclass with Brent Brooks and special guests from around the world. There are also details of our 5-day intensive tall building fire safety management course, which will be running in London throughout 2026, but also in the Mediterranean, in Cyprus and in Malta. This is an ideal course for anybody who's dealing with fire safety matters in tall and complex buildings. So I hope you find these videos useful. And as we say in the Tall Building Fire Safety Network, go high and go well. Thanks.
I'm following those two very digital presentations. This is very analog.
Well, I mean, you've mentioned the golden thread, but I think just
Right, thank you very much indeed. I've been asked to talk about toxicity today, and this stems from some work we did following the Grenfell tragedy, where we wanted to understand things a little bit better preemptively. So this work was conducted while I was at FPA, the Fire Protection Association, where I was the technical director. It was funded by ABI, the Association of British Insurers, and with great involvement from the University of Central Lancashire. This work we referenced tomorrow in Ed Gallier's talk, I understand, where I think he's used some of the results to do some very valuable modelling. So really, obviously, there's a little bit of a then and now to this. When it comes to toxicity and life lost to fire, once upon a time, the majority of life lost to fire was from death from burns. But with the introduction of things like furniture regulations and the like, the majority of lives are now lost to being overcome by toxic smoke. And the key assumption here is really that the source of fuel, and by definition, the source of potentially toxic smoke, really stem from the contents of a room in the spaces that we actually occupy. And so to this end, this is where legislation has focused, and we have our furnishing regulations and electrical and gas supply regulations, strict controls on those. But I think it's important to look at what this actually sort of implies in full. When you actually see what this implies, you end up with a sort of bullet point list, which is fairly straightforward. Fires only really start and travel within the building. Only the contents of the living space provide the fuel and are relevant to human health. The empty living space itself is non-combustible and therefore no toxic threat. The construction materials do not participate in fire to cause harm to occupants before evacuation. That the compartmentation integrity of external walls, which aren't really defined as compartment walls in terms of fire terms, a fire boundary, is irrelevant to any likely fire scenario. The windows and penetrations through exterior walls do not compromise the fire safety or reduce time available to escape. So this is the sort of wisdom of the years, and nothing has changed. But has it? Now, when you actually look through the recently released Grenfell Phase 2 reports, an assessment is made of the immediacy of threat to occupants from toxic smoke, and most importantly, from its origins. And the conclusion there that was made, that was contrary to accepted contents first model, first exposure to toxic smoke by those seeking to flee had its origins within the insulation and window frame materials of the external wall, introduced through the fire soft features, which are really the windows, the detailings, the vents like that, penetrations through the facade itself. And it was only later that the contents of the rooms and the living spaces acted to threaten the lives of those still trapped. Now this turns everything on its head, because when you actually review our bullet list that we've just been through, what does that actually mean? Well, actually, when we look at the assumption here, first of all, fires only start and travel within the building, things which are relevant to life safety. Well, clearly that's not the case when you have mass fire spread over buildings. We also need to think about other modern building methods, like modular, which can introduce very complex voids around every surface, and which even connect through to the rain screen facade. So there are now multiple paths for fire spread, and with that, the transport of toxic byproducts. Only the contents of the living space provide fuel and are relevant to human health. Well, clearly that's not true. The empty living space itself is non-combustible. That may be true. But certainly construction materials do not participate in fire to cause death or harm to occupants before evacuation. Clearly that was not the case in Grenfell. And the compartment integrity of external walls really proved to be a very key facet in this, that there was a connect between occupants and the building materials on the external of that building, which were very relevant indeed. And with that, obviously, a key to that were the access provided through the windows and penetrations through the exterior walls did compromise fire safety and reduce time for escape. So with that in view, if we've established that there may be circumstances where toxicity is an important factor for life safety and escape, particularly where you're remote from help and escape might be difficult, then we need to look at it in more detail. But toxicity itself is quite a complex thing. We need to know very much what the source materials are. As I'll show you today, we need to know how and why they are, how and where they are burning, what the toxic components are, what the routes are for contact with people, and what factors ultimately, as a resulting from the toxicity, will impact the ability to escape, the time to incapacitation of people, and time for lethality. And it is quite complicated. Now, what do we mean by toxic threat? If we just look very simply, it comes down to a number of things. Most simply, production of smoke causes loss of visibility, which may hinder escape. But then we also have irritant products in there, which may irritate the eyes, the lungs. This may hinder escape. Things like hydrochloric acid, formaldehyde, acrolein. These are all products which can be generated from under the action of fire from many products. We also have the poisons, and these are which lead to asphyxiation. The core one being carbon monoxide, and this simply takes, as I'm sure you all know from smoking commercials, will really take the place permanently of oxygen in hemoglobin of the blood, thereby depriving the body. And we have materials like hydrogen cyanide as well, which prevents the use of oxygen by the body's cells. We also have gases which stimulate respiration, like carbon dioxide. So when you're in this rather bad atmosphere, it's making you breathe a lot faster, so the rate of deterioration of someone might be faster. And also we might be in quite a reduced oxygen atmosphere because it's also consumed by the fire. And then, probably less relevant to this talk, but we have the sort of a longer-term toxicity, toxic materials for humans, the particulates, carcinogens, and endocrine disruptors. These are the sorts of things which no doubt you've heard Anna Steck talk on at some time, but if you want to know more about that, please do refer to her papers on it. So we've established now, how some factors which contributed to the death of people and what the toxic threats are. How did they actually come into contact with it? Well, actually, the external envelope of a building is not considered a fire compartment boundary, and as such, there's no sort of requirements to fire stop penetrations. So if you think of something like a sort of kitchen duct or something like that, between maybe this room and a corridor, an escape route, that will have very defined detailings to ensure that you preserve the fire integrity of that wall. But if that same duct is put in this wall to the outside, the same rules don't apply. It's not considered part of the fire fire compartment. That's not to say that sometimes they're not. So there's no requirement, and also in the testing of facades, of the infamous BS 8414 testing, there's no requirement to understand how penetration of the cladding by ducts will impact the fire test in terms of fire spread or anything else for that matter, such as the transfer of toxicity. And this is what we undertook to look at. You can see in this picture here on the right-hand side the sort of ducts that come through this cladding here. Really, it's surprising the way these are sometimes implemented. Sometimes they actually just open out into the cavity, and there may be just a few slots cut in the rain screen itself. I've seen instances where there's not even that, where actually you are venting into this cavity, which is a very strange thing to do. And when you think about ingress and egress of fire potential, it's a very stupid thing to do also. But these are all the sorts of things that have sort of lacked thought and guidance. But these sorts of features play no part in 8414 testing. But we thought we'd look at it. But when you actually break down what you're looking at that might be relevant to toxicity, we made the decision to test for toxicity in two places. Obviously, we had our rig in a sort of fire laboratory test room. Now, we can just look at the general smoke layer that accumulates at the top of the building. That's one thing. That's fine, and we certainly did that. But there you're measuring basically the products of combustion which have burned in a good and highly ventilated oxygen environment, just like having a bonfire of parts. But actually, we know that the route for communication is through these voids here. And so you'll see a few arrows there coming up on the left-hand side diagram up through the vent. So it's very important for us to know the difference of how things burn in a void rather than out in the open. So we measured things in a number of situations. And in the right-hand diagram, you see a sort of a crude drawing of our experimental test facility, where we measured what came out in the extract duct. But more importantly, we saw what came out in the duct, oversized as it's drawn there, with products delivered from the rain screen void itself. Now, what led us to look at this? Well, here's some historic work from Professor Richard Hull and Anna Steck from UCLan, who are very knowledgeable on all things toxicity. And they undertook a study of different insulating materials which were combusted at different levels of oxygen ventilation. So these figures along the bottom, they look at they refer to well, small and large under ventilation. And what you see if you look at the first row for PIR materials, as you reduce the amount of available oxygen or increase the amount of under ventilation, you'll see that the toxic threat of the products that are evolved in that situation go up quite significantly. Now, the left-hand sort of margin there is FED, which stands for fractional effective dose, and that is a measure of time to incapacitation or death of someone of 50% of a healthy human population, and a number over 1 is where incapacitation or death may occur. I don't know the details of this specific diagram. I'd need to look back. But these are the sorts of analysis that we use in this study. So what you need to take away from this slide is when you start to burn things in underventilated conditions, the level of toxicity rises pretty enormously. Now, at the Fire Protection Association at the time, we had the benefit of lovely big labs. There was another purpose to doing these tests in that we replicated some of the government tests that were done because we had some concerns about the way that the panels were sort of fixed in place. They seemed to be a little bit over-engineered from what might be considered normal from the engineers that we spoke to, from the facade engineers that we spoke to. So these tests served a number of purposes, but we did 4 tests on a mini cut-down rig, stone wall insulation with an A2 ACM panel, a PIR insulated system with a same panel, and a phenolic insulated system with an A2 ACM panel. And then the final test, we looked at really tried to replicate the materials that were on Grenfell at the time to see how we would get on. And here are a few. On that left-hand picture, on the top left-hand corner there, you'll see a vent that's been fitted. It has all the correct cavity barriers in there, so they've been correctly built. So this was the stone wall insulation, and you can see the level of destruction done at the end and how the fire progresses. The PIR insulation, similarly, obviously it burns away and panels fall away. With the fixing method that they have, it is only aluminium, obviously. And then we had the phenolic. Okay, so these tests all look rather similar. Then we came to the Grenfell recreation that we did. I'm afraid we could only run this test for 12 minutes. Beyond a no doubt, those materials are absolutely dreadful, and they are different to all the 3 in terms of what I've showed you before with the PE panel rather than the... so this is a non-fire resisting ACM panel. It was a disastrous test in terms of, and we had to stop it very, very prematurely indeed. I think you'll see from that middle picture how much burning material is falling in liquid form onto the floor there. And, you know, of course, this is at the root of the Grenfell problem. These are materials which are traditionally used just for road signs, motorway road signs and things like that, not originally meant for putting on buildings, but that's where they ended up. So the type of results that we got from this, if we just look at the 2 crucial things that we used to measure fractional effective dose of carbon monoxide and hydrogen cyanide, but the concentration that the kitchen duct was up to, the kitchen duct simulation that we had in there was up to 100 times that measured from open burning. So here we start to see why there can be such a high toxic threat of occupants directly exposed from these rain screen designs with inappropriate materials and inappropriate fire stopping or separation of them from those materials. So we measured oxygen concentrations in that void as well, and obviously they're very much lower. We also did the same test for hydrogen cyanide, and we got pretty similar results to that in that in the kitchen duct itself of hydrogen cyanide we had 28 times that measured from open burning, and we again saw a similar pattern of how the various combinations of materials actually performed in this. Obviously the combustible insulations gave a response, and very little from the non-combustible insulation that we had in there at the time. So now let's talk about fractional effective dose, really just to finish off. The toxic effects of fire effluent can be expressed as a fractional effective dose based on the chemical composition of the effluent. If you want any further reading on this, have a look at the papers from David Purser, who I believe gave birth to all of this as an understanding and a method. When the fractional effective dose is equal to 1, 50% of healthy adult exposed population would be predicted to suffer incapacitation or death. The top graph there shows the FED for incapacitation. You need to take these results for the exposure in a given volume. And so we chose a 50 cubic metre room, which might be in a kitchen or a bathroom where someone might be taking refuge. And you can see after a relatively short period of time, certainly we see the PIR with the A2 ACM panel could be expected to render someone unconscious. And we have a range of results, and certainly when it comes to incapacitation and death, that can follow soon after. So I'd probably conclude in that purple box there that really for a 50 cubic metre room connected to the rain screen void by a 100 millimetre vent, the results suggest that for some material combinations, ones with higher combustible content, incapacitation can occur in around 10 minutes after the fire breaks into the location of the cladding system containing the vent. And for the other ones, that's sort of 7, 22 and 29 minutes, respectively. And if they cannot escape before becoming unconscious, the death may follow within 30 minutes, if not rescued. I think this was quite a startling finding, and I think you'll understand from Ed Galea that tomorrow he may be showing you results a little more worrisome than this. But it starts to explain some of the terrible things you hear about the Grenfell situation, people expiring while on the phone and their flat was not on fire. So really, just to conclude and to wrap up, the Grenfell Phase 2 findings tell us that at a height where probably evacuation is difficult and where help is remote, circumstances can arise where there is a need for the building materials selection to better support life than in situations where escape is easier. Now, this is common practice in many other situations to do with transport. As I mentioned, I do a lot of work for the military on ships and submarines, and certainly the inventory of materials and the evaluation of the toxicity, their toxic threat that they present, is an absolutely integral part of their selection as being fit for purpose. Obviously, people who are very well aware of this, certainly London Underground, shipping, submarines, aircraft, all tightly controlled. Now, when you think about it, what's the difference between someone who is up high in a building versus that's on fire versus someone that's deep down in a submarine that has a fire? There's very little difference, actually, at the end of the day. They're remote from help. Escape and evacuation might be impossible or difficult. So really, it's a consideration that maybe there is a situation and a scenario where building material selection should include a consideration of toxicity going forward. And then what we need to respond to that is, do we have the appropriate test to do that? As I say, and this is what certainly the likes of Richard Hull have been working very hard on, so that we can actually test materials in the oxygen level environment that they like to experience at the end of the day, to get a proper true reading of how they are going to perform in the end scenario.